thanks so much for coming today. It's great to see as COVID disappears that we have like growing crowds here, and it's great to see all of you. Welcome also to everyone who is attending us online. It is my great pleasure to welcome once again Roberto Calandra to Toronto. Roberto, it's super cool that you're here. I don't want to make this introduction long. A few words about Roberto. He has been working and is currently working with Meta AI research, but he has an amazing academic career, and you've been doing amazing work and working with many great people. Having done his PhD with Jan Peters in Darmstadt, a very famous roboticist, and then in Berkeley, you've been in Sergey Levine's group, right? So had amazing collaborators throughout. It is super cool to have you now here visit us, and more recently, you've been interested in touch and perceiving, understanding, and interacting with the world through touch. And I very much look forward to your talk. Thanks so much for being with us.
Thank you. So, hello everyone. Thank you, Igor, for inviting me, and thank you, Toronto, for hosting me. It's a great pleasure to be here today. And today I'm going to talk about a topic I've been very passionate for a few years now, which is touch. And if you are interested, slides are also available online if you want to go back at a later time. So let me start by saying a word of essentially where I come from, what's my background. Now, I'm really working at the conjunction between machine learning and robotics. And for me, one of the main motivation of machine learning is the fact that we have seen in recent years some pretty impressive results in being able to use AI to solve control problems, to solve things like the game of Go. And at the same time, it's very hard still to use this type of algorithms into the real world, in real world applications. And so some of the fundamental questions I'm generally interested in answering is how can we scale this type of algorithms and this kind of control structures to more complex unstructured domains. Domains that can be things like robotics, decision-making, finance, and biological sciences. But specifically, what I'm mostly interested in is robotics. At the core, I consider myself a robotician, and the reason why I love robotics is because I believe that robotics has a huge potential for being beneficial to our society. I would really like to see robots in 10, 20, 30 years being able to automate industry much more than we do today. If you think that there are still hundreds of thousands of kids working in coal factories in Thailand, well, I would like to remove these jobs from the future. I don't think this is necessary. I think we, as a society, should be able to move beyond having this type of manual jobs. I would like to see robots being useful in disaster reliefs, especially with arguably climate changes. We see more and more disasters. Well, we maybe should use more robots to be helpful for people. Exploration is super interesting. We already send robots to the depth of our oceans and to the heights of other planets. And these are environments which are extremely difficult for humans to be and to operate. So robots will be crucial for this type of explorations. And finally, medicine and eldercare. With a growing older population, especially in the Western societies, we will need more and more robots to assist our elders and to improve the quality of our general healthcare systems. And however, if we look at what is the state of robotics nowadays, this is a video taken in 2015 from the DARPA Challenge. The DARPA Challenge, for the one that don't know about it, was like the most competitive robotic, big challenge, and there were dozens of the best team in the world spending years and years, and in some cases with teams of hundreds of people working on having these complex robots, essentially being able to solve some sort of task and going through some sort of path with different obstacles. And if we now look at this type of robots and their behaviors and their failures, this is qualitatively stupid. Any kids that is 3 years old is not going to fail in this type of silly ways as these robots are doing. And now all of these robots are really the state of the art of what we can do today, meaning 5 years ago. But how can we move beyond that? How can we have systems that are more intelligent, are more adaptive, and can do better? And I believe that in order to be able to have robots ultimately being used in a wider number of environments, including homes, we need to have robots that are capable of adapting. We need to have robots that are more secure, that can interact in a meaningful but also safe way with humans. And my personal opinion is that machine learning is an excellent tool to go beyond sort of what is the state of the art and to make robots smarter and more useful in the real world. Now, there are a number of challenges that we need to do in order to be able to actually do and achieve this type of high-level goal. And these challenges are really spread, in my opinion, across the whole spectrum from hardware to the control scheme that we use to the type of high-level planning and software that we employ for decision making. And some of the topics that I'm generally interested in include multimodal sensing, hardware design, and adaptation to new tasks. And some of you might be quite familiar with my work on model-based reinforcement learning, but today I'm instead going to talk about a different topic, which is touch sensing, as a way to include multimodal sensing and provide robots with more information about the world in which they operate. So, let's talk about touch. Touch is probably the most important sense that we use in our everyday life, although we barely realize it. Touch is not only the most ancient of the senses that developed throughout evolution, but it's also the sense that allows us to measure forces. And in a world dominated by the second law of, by physics, understanding force means understand the world, means be able to control the interactions that we have with the environment, means balancing as we step on our feet, means being able to keep an object in your fingers without it slipping. And we have a lot of evidence from physiology that touch is important in humans, and without touch, we fail. This is a video from Ronald Johansson's lab, where they would essentially ask people to solve very simple tasks, and then they would anesthetize their sense of touch while keeping their motor control capabilities. And suddenly, very simple tasks like lighting a match would become extremely difficult. And the reason is because although we don't fully realize it, we do use touch extensively in our motor control capabilities every day. From lighting a match to searching for your phone at night in the dark. So, what is the problem of touch? Why don't we have touch in every robot that is produced and sold nowadays? The reason is because historically, touch sensing is a very hard field, and it's intrinsically an interdisciplinary field that goes along different levels of our essentially vertical stack. Because you have hardware design of sensing, of tactile sensors, then you need to process these informations, you need to integrate this sensor modality into your control scheme, and ultimately you need to use it into an application. And historically, touch, different labs, sort of in the last 4 decades, have been focusing at different levels of this vertical stack, but nobody has really been able to work on all of this, simply because it requires a huge amount of expertise for a single lab to be able to do this, and because there is virtually no reusability in essentially the solution that we find at the moment in tactile sensing technology. Most of the lab, there are hundreds and thousands of really cool prototypes of tactile sensors that maybe there is one built during a PhD, and then that would be just shelf, and nobody else would ever use it ever again. So this is, of course, not a good thing for science because it doesn't enable the researchers to build on top of others' people's work, and we essentially keep reinventing the wheels over and over again. And also means that there is a very high entrance bar for new researchers in this field, because if you want to work on tactile sensors, you first need to know how to build a tactile sensor, which is, its own huge, deep problem. So some of the questions that I'm interested in sort of trying to answer for further science in this field is how can we lower the entrance bar for new researchers in touch sensing? How can we improve reproducibility? And how can we accelerate ultimately research through the reuse of different components? And a big part of what I'm going to try to sort of show you today is that in order to do all of these things, it's necessary standardization, and it's necessary the creation of an ecosystem of tools that can be reused and shared and developed by the whole community in order to accelerate research further. So, and thinking about touch, the way that I'm thinking about this field is maybe a little bit different from other people, and I want to give you the way that really I'm thinking about it. Because if we compare to other fields in the past, we see that, for example, the mass introduction of telephones at the end of the 1800s really enabled the creation of new fields of computational science, enabled fields like audio processing, digital signal processing. And this was possible because suddenly we have telephones everywhere, and we need to understand what are the principles that guide the transmission of audio and the replaying of audio. And really, we want to digitize this ultimately at some point, and later on in the last decades, we also want to make use of machine learning in order to process this data and make sense out of them. Now, similar trend has happened in the 90s with the introduction of digital cameras, of cheap digital cameras. Now, everybody can take a phone, you have a digital camera, you can take a picture, you can record the picture, you can process this picture, you can transfer it over the internet, and you can essentially play it back on the other side of the world. And this is possible because a field of computational science have been dedicated to understanding vision, processing vision as a sensor modality, and more recently with extremely successful fields like computer vision, you can now even create new images out of nowhere. And I believe that we are now at the point where touch sensing is already and will become more and more widely available in the very near future. And this wide availability of tactile sensors will inevitably lead to the creation of a field of computational science dedicated to the processing, digitalization of touch as a sensor modality, and then the processing and ultimately the reproduction of touch at a distance. And this field that we call touch processing will have to deal with the same problematics that other fields in the past have done and dealt with, of how do we make sense of a new sensor modality with specific structure and problematics. And now, in order to deal with all of this, we have been essentially dividing our grand vision of touch under 4 main pillars. And these 4 pillars are hardware, touch processing, simulation, and benchmark and dataset. In addition to this, I will also be talking today a little bit about applications, which is ultimately what drive a lot of the research that we've been doing, especially in robotics, and community. The idea that we want to build a community and we want to provide tools for a community to grow into this field of touch sensing. So let's start from hardware. There have been, over the last few decades, as I already mentioned, many different types of tactile sensors, but most of them have been stayed at the stage of prototypes, and only a handful really made it into the market as a commercial product that you can go out and buy. Some of the most important factors when we want to evaluate tactile sensors are availability, how easy it's for me to buy one or to build one, cost, how much does it cost to buy a tactile sensor? Is it going to be thousands of dollars, or can I buy a cheap one for $2? form factor. Is this going to be in the form of a finger? Is this going to look like a skin? Or what are the mechanical properties? Capabilities. So what am I measuring? Am I measuring forces? Am I measuring normal forces, friction? What can I see? What can I sense from the world through my sensors? And at what resolution? And ultimately, reliability. This is extremely important because if we think about touch in contrast with other senses, touch is a sense that naturally and inevitably assume and need the physical interactions with other objects, physical interaction with the world around us. And this implies the fact that any tactile sensor will have extremely high wear and tear compared to, for example, a camera. Now, nature, from this point of view, it's amazing because our tactile sensors are self-regenerating. And if you cut your finger, it will grow back in a couple of days and it will heal, and that's great. But in the moment when we build physical sensors, we are not at the stage where these technologies are ready for a self-healing sensor. So we need to make sure that any sensor is able to withstand hundreds of thousands of grasp or interaction with the environment around us. And now, the type of technology that I'll be talking today mostly fall under the concept of vision-based tactile sensors. This is a technology that was proposed already in the 70s and 80s, but recently was sort of rediscovered and a little bit more made popular by the work of Ted Edelson at MIT. And the basic idea is very simple. We essentially have a piece of silicon or elastomer, and below this elastomer we have structured light, typically RGB LEDs, that shine onto this elastomer. Now, whenever a contact happens between an elastomer and an external object, this is going to deform the elastomer and is going to create shadows of different light and color patterns and cues that will be recorded by essentially a camera that lay inside the sensor. Now, this technology is great because it has virtually no moving part compared to capacitive or resistive technologies that have been used in the past. And it's very cheap to produce, and it's fairly robust because the only part that is in contact with the external world, it's a piece of silicon. And we know fairly well how to make silicon that is hard enough. So, using this type of technology, in 2020, we designed an open source digit, which is the first mass manufacturable, low cost, and high-resolution vision-based tactile sensor. This sensor was really designed with the idea in mind that we want to be able to democratize touch, and as such, it was designed so that it's extremely easy to build. You can essentially 3D print it if you have a 3D printer in your home. You can buy a couple of pieces of electronics, and you can essentially put it together with minimal knowledge of how a tactile sensor actually works. And it's a USB, so you just plug it in your computer, and basically you work out of the box. Now, this was an extremely popular sensor, and part of this is the fact that it provides extremely high resolution images about the object that we are touching. It's compared to other tactile sensor technologies, this is going to give us hundreds of thousands or millions of pixels of resolution of what we are touching, down to a spatial resolution of about 20 micron, which means that if you touch a hair, you can actually see the individual sort of strain of your hair. And this is super cool, because now we can sense the world, we can sense the geometry of how the world is, and indirectly we can also compute the forces that elicited this type of deformation of the silicon. And what's most cool is that if we compare this type of sensor to the leading tactile sensor sort of commercial product available, which is the biotech, we see how we essentially have 3 orders of magnitude more pixels of resolution, and it's at the same time 3 times cheaper to manufacture, which means that we can now have a lot of these things and have better performance for the same price of a single sensor, from $15,000 to $15,000. And of course, this is open source, so anybody can just download the schematics and build it at home. Now, even so, if you want to build it at home, there is, in practice, some level of expertise that is necessary in order to do so. And we have seen already over 20 universities replicating our sensors, but something that we are extremely proud of is that last year we partnered with a startup called JetSet Inc. To actually commercialize these sensors. So everybody now can go to the website of JetSet and can buy one for $300. And in the first 10 months, we have, they sold over 1,000 of them, which makes Digit the most sold high-resolution tactile sensor in the world. And this is really pushing more and more researchers to work in this field, because now it's, working tactile sensing, even if you do machine learning, is as easy as ordering something online, waiting it comes to you in your mailbox, and then use it for whatever applications you care about. Now, once we have hardware, the next level is simulation. Simulation is an important part of our research workflow as researcher, because allow us to prototype and to test things without having to deal with the physical artifact of our work, and in some cases also to be faster in the prototyping loop. Now, one problem with typical tactile sensor simulators is that simulating high-resolution tactile sensors is extremely difficult, because most simulators become slower and slower the more contact points you have for the way that they essentially solve the equations of dynamics. And this means that if we want to have already over 1,000 contact points, any simulators that you find at the moment around would become slower than real time, and therefore less useful than it is. So, and Digit has 300,000 contact points, so it would be extremely slow. So one of the things that we did 2 years ago was to open source a fast simulator that is capable of reproducing and simulating vision-based tactile sensors at hundreds of hertz, even for extremely high dimensional output from the sensor. And now, the nice things of this is not only that it's open source, but it's also the fact that it can be plugged into physics engines of your liking. So you can use PyBullet, you can use Joko or Isaac Sim, as long as you can extract the geometry of the object that you're touching and the amount of force, you can essentially plug it into tactile and render your favorite vision-based tactile sensors very fast and very easy. And here, for example, we show omnidirectional tactile sensor called OmniTac, and here there is a multi-finger hand with different digits mounted. In addition to this, the simulator can actually be tuned with respect to a real digit sensor and can be made extremely realistic. So in here you can see images from the simulation on top and the corresponding image at the bottom. And they're qualitatively fairly accurate. Now, this doesn't actually simulate or deal with the problem of how do we simulate a flexible body and the interaction of the dynamics of a flexible body. But at least from the optical rendering points of view, this is an extremely nice simulator, and again, very fast and fairly accurate. So, once we have a hardware and we have simulation, what do we make of these high-dimensional images and outputs that we get from a sensor or from our simulator? So the next step is going to be processing. How do we make sense of touch? And now, this is a very important problem, but it's also a field of where there is extremely limited literature. Partially it's because we haven't really seen such high-resolution tactile sensors before now, but partially it's also because there haven't been enough sort of time and interest in going into some of these questions. So I really strongly believe here that what we will see in the coming years is this creation of this new field of computational science of touch processing dedicated to touch in the same way that computer vision is for vision and natural language processing is for audio. And some of the obvious questions that people will try to answer are things like, what are good features for touch? Can we then represent a generalizable representation in the same way that we can do for computer vision? What type of standardization do we need for the sensors? Vision, we know that we have 2D structures. Is it the same for touch, or do we need more? And also, what are the useful structure in the computational models? In the models that we now train for vision, we know that we have a very strong geometrical structures that we can impose over the models to make it working better. In the same way, for natural language processing, we know that there is a temporal structure in the problem. What are the type of priors and inductive biases that we can have for touch, which is a sense which is both spatially and temporally highly correlated. And as our first step to starting to tackle this problem, we open source as a part of our ecosystem of tactile sensors and simulations, also PyTouch, which is the first machine learning library dedicated to touch processing. And the idea is that by providing a standardized framework, we are now able to start comparing different models and switching different models to evaluate how they work, what are the important aspects, what are the important features. And also this one is, of course, open source. And more and more people are now adopting this framework, including companies that sell sensors, so that it's easy to deploy machine learning models in practice on tactile sensors. And really, one of the goals that we want to have here is that we want to create the equivalent of OpenCV for touch, where anybody without any prior knowledge about machine learning can just connect the sensor to their computer, download PyTouch, download a pre-trained model, and use it very easily, very seamlessly, and essentially deploy it so that they can then work on higher level applications where they can exploit the fact that there are already models that can do different tasks and solve different problems. So some of the features of PyTouch is that it's hardware agnostic, it has native integration with Digit, but also the fact that it's really touch as a service, where you can essentially have a library of models, and depending from your sensors that you have, you can directly download this model and enable you to do different things. For example, here there is a snippet of code where we essentially, in 3 lines, we are now connecting a Digit sensor. We are automatically downloading a touch detector model from the cloud, and then we are querying whether the sensor that is connected to the computer is actually touching an object or not. And this is done, in 3 lines of code, and anybody that, even people that have no experience with machine learning or tactile sensing can essentially run this. Now, this also, of course, enables us to start answering some of the important questions about touch processing and features in representation. And just to give you 2 examples, one of the things that we started to evaluate is whether the features that we can learn from these vision-based tactile sensors are generalizable between different models of vision-based tactile sensor or across similar sensors from the same family. And the answer seems to be that yes, if we actually train model jointly across different sensors, this seems to be learning some useful feature of touching, and this provides better performance compared to training a single model from a single sensor. And at the same time, we recently put on archive a paper about being able also to learn reusable vision tactile representation, where by matching the visual appearance and the touch in a sort of task agnostic way, we can then reuse this representation that we've learned and apply them to 5 different tasks, including anomaly detection and tactile servoing. And the performance of using this sort of pre-learned features in representation is actually provide performance which are better than trained exclusively on supervised data from that one particular task, which I think is very cool and sort of really aim at the fact that we will be in the future likely to be able to learn features that are like ImageNet of touch. Something that you can just download and use it for essentially retrain your model, and this is going to actually be useful and helpful in our workflow. Finally, I'll be talking very briefly about benchmarking datasets. Benchmarking datasets are really the blood of science. Benchmarks are super important to measure progress and to make sure that there is actually an advancement of science over time. And as a community in tactile sensing, benchmark is something that we are very much lacking at the moment. There is no agreement of what are useful benchmark. There is no agreement of even at what level of abstraction we really want to benchmark things. And by now having standardized hardware and accurate touch simulators, we can now start thinking about these benchmarks, because we have the tools that both people in hardware and people that only work in simulation can start to benchmark their algorithms and potentially their hardware design. And at the same time, once we start thinking about benchmark, we can also start thinking about datasets. Because nowadays we have extremely limited datasets that are publicly available about touch. And this has been mostly because of the limited reliability of hardware. It was not possible to collect datasets of hundreds of thousands of interactions, but now we can. So the next step as a community is that we really should be engaging and start to build this large-scale dataset that can be helpful and useful for the whole community. And as a very, very tiny sort of step in this direction, we, in Tacto, we essentially design a very small sort of benchmarking dataset of a robot hand grasping a single object. And we were able to collect over 1 million grasps of this robot, and then train different grasp stability predictors, essentially that predicts whether the object is going to be still in my hands after I lift it, or whether it's going to fall down. And now the important thing is that this enables us to start thinking about comparing, for example, different vision. Is vision, going to be useful, or can I get away just using touch? And the largest publicly available dataset before that was 6,000 grasps. And now with 1 million, we are talking about different order of magnitude larger. So we can start to evaluate models at a completely different scale with different properties. And this is extremely important because it enables us to do things that were not previously possible from, again, publicly available datasets. Now, I now want to spend 5 more minutes before concluding about applications. Why is touch useful, and what are the applications where touch can really make a difference? I believe that touch has a lot of really important applications that would benefit from it. And I will not go into details in all of them, but at least I want to give you, sort of a personal opinion of some of them. Now, some of them are kind of obvious prosthesis. If we can provide the sense of touch back to people that lost their limbs, whether it's arms, whether it's feet, this is likely to improve their quality of life significantly, as well as their motor control capabilities, as we have seen, for example, from the skill of the Latina match. Another field where it's likely that touch will be an important role is metaverse or telepresence. And I'll spend a little bit more time on this later. Another field is e-commerce. With our phone, we are now capable of taking a picture of an object and say, hey, search for an object that looks like this, and you can buy it online. Why not having a tactile sensor like Digit, touching your sweater and say, hey, buy me a sweater that feels like this, or that uses the same thread or the same material, or that is as soft as my favorite sweater. And I think that in the future, once the cost of tactile sensors will decrease, we will get there ultimately. And finally, robotics. In robotics, there are almost endless possibilities. From home robotics, where if we want to have robots in our kitchen, we need to make sure that they are able to sense forces and interact safely with people, but also agricultural robotics, things like grasping a strawberry, If you don't have the intuition of how much force you're applying when grasping a strawberry, you're going to squish it. In the moment when you can measure forces, you have tactile sensors, then it becomes almost trivial to pick up a strawberry because you know how to balance forces and you can measure them. And again, things like medicine robotics, where we can foresee in the future that surgeons doing teleoperations should be able to sense force in the moment when they're cutting a patient which is dozens of miles away, or potentially also diagnostic sort of applications like breast cancer detection through palpation or palpation of the abdomen, which is still very much done manually nowadays from doctors. So these are just some of the applications that I found personally more fascinating, but you can imagine that there is much more than this. And specifically about sort of teleoperation, if you think about it, touch is actually one of the most deeply social and emotional senses. There is nothing that compared to being able to actually touch a loved one or hugging your grandmother. Vision, smell, they are not so deeply instinctive in the same way that touch is. And being able to really sense, calibrate, and reproduce touch over the distance would be extremely beneficial for any type of, sort of human interaction over sort of internet. And of course, we can also use touch to accurately and easily digitize objects into any type of virtual reality world, where some of the properties of the object around us can only be sensed by touch. So like things like deformation, softness, and material properties. And so really, where I see touch is in this part here, where touch can be used for sensing the interactions of our tactile sensors, and ultimately process informations through touch processing. Of course, how to reproduce touch is then a completely different field, which is its own problems, and I'm not going to go into optics, that's not my field. But just to give you a sort of cute example of a paper that we did almost a decade ago, we had in Darmstadt during my PhD a full humanoid robot called ICAP, where we essentially were teleoperating through a very natural and intuitive setup, where the operator was looking through the eyes of the robot using Oculus Rift, and by moving its head was controlling the eyes and the neck of the robot. And then we had a very simple optic gloves where you could feel through the tactile sensors that what the fingertips were touching of the robot, and at the same time you could control all the joints. And finally, through our Kinect, we were mapping the skeleton and control the rest of the whole body kinematic of the robot. And this was done almost a decade ago. So with the current technologies and current sensors, I'm sure that we could do much, much better than this. And of course, there are many more people working on this than me. So finally, robot learning. I want to spend my very last slides about talking about how touch is important for robots and how learning fits into this. Over the years, we've been working on a number of papers that sort of try to use touch for a number of different tasks. Some of these things are like how can we predict whether a grasp is going to be stable, or how can we decide where to grasp or regrasp an object by using touch. And in these papers, we have very strong evidence that using touch actually help this type of grasping task compared to only using vision, quite substantially so in fact. We also can imagine that touch is important to identify objects. If you are searching inside a drawer, you are able to recognize which object is which, or which one is, if you are searching for scissors, you can find them just by touch. And you can associate in your mind, oh, this is how it would look like. And finally, active tactile exploration, both from just touch and from vision and touch. So how can I reconstruct the 3D shape of an object if I cannot see it, or if I can see it, but I can also have touch sensors that gives me very high resolution information locally, in contrast to the global informations that vision is giving me, but that might not be so accurate. And recently, actually in 2 weeks, we will be presenting at IROS a cool paper about learning to play piano in simulation using touch. If any of you play instruments, you know how important it is to be able to sense the interaction with the instrument, whether it's a string or whether it's a key. And by using touch, we are able to essentially modulate time and the sound better than without using touch, using reinforcement learning. And touch is also crucial for very fine manipulation. In this paper, we learn how to essentially manipulate a small a glass marble between 2 fingers without have it dropped. And this is an extremely difficult task for robots because it's actually not, the dynamics between the fingers and the marble is very difficult to model, and you need to do really fine manipulation. So the way that we approach this problem is through model-based reinforcement learning, where we essentially learn, given 2 images of what we are touching, how these images are going to change into the future if we were to apply a specific actions to the finger, and therefore then we do the inverse optimization of deciding what is the set of actions that will bring me closer to the desired outcome. And this actually works extremely well in practice, or well, fairly well. Sometimes it still falls down the marbles, but it has the capability of avoiding to squeeze too hard and the marble shooting out, as well as losing the marble because you are not applying enough force. Now, ultimately, what we would like to have into the future is to, of course, be able to reproduce the dexterity of human hands. And this will require in the future both the design of better hardware for robotic hands, but it's also likely to require the use of better tactile sensors to be able to sense the state of the world and the interactions that we have and the forces that we have with different objects. However, as a counter-argument, you could actually think that, do we actually really need touch? And just 2 days ago, we released a paper where we essentially learned how to manipulate and rotate in hand over a few dozens of different objects, but just using sim to real, without the use of any tactile sensor information, without the use of any vision information, just through proprioceptive feedback. And although this is an extremely interesting results, because it really shows the sort of how far we can go away, with manipulating object just by using finger informations of the position. But it also shows very clear hints of how can we make this better, because there are very obviously corner cases where we see that, for example, the hand is not able to recognize the geometry of the object that is touching, and that's where we will need touch. And also for tasks that are more dynamic. Questions?
Does this case have torque feedback? Does it have torque feedback?
It does have feedback. It's not torque feedback, it's position feedback.
So it doesn't even know about forces?
Correct, yes. Well, you can argue that indirectly through the position, and knowing what's your action, which is also position, you can reconstruct the torque, because the underlying controller is a PID, so you know what are the questions. But yes, it's in theory, technically speaking, it's position control. And this is online, so if you're interested, you can go and read it. So to conclude, if you're interested in tactile sensing, there is a Slack channel for the tactile sensing community at touchsensing.org, and I encourage you to join it if this is the field where you want to do research. And I really want to thank all the collaborators that have been working with me on this over the years. All of this work is possible because of the amazing collaborators that help you in every day and keep you going even when you don't like it, or sometimes you wake up in the morning and you're depressed. And in particularly, I want to thank Mike, who has been leading some of the technical efforts on the design of Digit and of PyTouch. He's sort of has been my partner in crime for the last couple of years on touch sensing. So to conclude, what I hope I convey today is the fact that touch is a key sensor modality, both in humans and robots. And over the last few years, we've been trying to create this open source ecosystem that can hopefully reduce the entry bar for new researchers in the field and can help with simplifying the perception, understanding, and interaction through touch. And as a part of this ecosystem, we have now sort of cheap, reliable hardware. We have fast simulators, and we have machine learning libraries that can be used for processing the type of raw information out of the hardware. And we really have been aiming and trying to grow and support the community in their effort to further this field and accelerate research in this field, with a really long-term goal of making touch sensing practical and useful in the real world. 10 years down from now, I would like every single robot on the planet to be making use of touch and to have capabilities that are not possible today just from vision and high perceptive inputs. So thank you very much, and I'm happy to take questions. Here is a digit sensor if you want to pass it around. Yeah.
Thank you for the amazing talk. So you mentioned the 1 micron resolution. Is that enough to detect, let's say, powers when you're touching?
So Roberto, please repeat the question
Yes.
for those online.
Yeah. So the question was, can we go down to 1 micron and sense powder? It's actually about 15 to 20 micron. About powder, we've actually never tried. My hunch would be that if you apply sufficient force, so if you squeeze, for example, between two fingers, you might actually be able to sense interesting things. But we have never tried it, so you'll be the first one. You should tell us. Yes.
Also, thank you very much for the great talk. And also about the sensor, how sensible is it? Like how much force do you have to use? Like how much deformation would it be so that it detects?
Yes. So the question is how sensitive is the elastomer and how much force can the sensor sense? The answer is that this is actually up to you, in the sense that the sensor is designed to be. I haven't really. Let's see if I have a backup slide. Yes. Okay. So the elastomer is very easily to change. There is a single screw that allows you to replace the gel. Now this is useful for wear and tear once the gel wears out, but also enable you to essentially use the gel that is specifically tuned to your application. Because every particular gel can be essentially designed to have a different dynamic range, and depending whether you want to do very fine manipulation of maybe small screws, then you want to have a gel which is more sensitive, or if you want to be able to do something like, I don't know, picking up rocks, you need to have a gel which is maybe more reliable, which is able to sense higher forces. And the sensors that are sold by gel site are roughly tuned in the order of newtons, so that it's roughly equivalent to what a human finger would sense in everyday manipulation. But you can, and we did it in the past, you can do it more sensitive, or you can do it less sensitive, depending from the specific application that you care about. Yeah.
So I guess my question is a bit like broad. I apologize in advance. But I guess you've been comparing touch with vision and audio. And I guess one key difference is that with vision and audio, when you record data with your sensor, it's almost trivial to bring it back to like an intuitively interpretable form. So you record your camera and then put it on a screen and see it. And I guess that can induce a bias in how you use that data. And I guess it's more complex with touch.
Yep.
And how do you think that's going to affect the development of touch as a sensor in robotics?
Yeah, okay. Okay, summarizing this question is tough. The question is, reproducing vision and audio is simple. Reproducing touch is kind of hard. How is this going to influence the field? Now, I completely agree with you. I think that part of the problem is that at the moment we have very good tools to reproduce vision, a screen, and very good tools to reproduce audio, like a speaker or your phone. With touch, we don't have such tools yet to reproduce touch. I think that at some point in the future, hopefully the haptic community will give us better tools to be able to reproduce touch onto our fingers. But until then, I completely agree with you that if we look at an image from a tactile sensor, it's not obvious how this is interpreted. Now, to large extent, like this is an image. To large extent, the best answer I can give you is that if we use machine learning, in many cases we don't necessarily need to have explainable outputs from the sensor, because if you only care about being able to predict whether a grasp is successful or not, sort of ironically, with such high-dimensional input, the model that you train with machine learning might actually be better than a human at recognizing what's happening. And part of this is the fact that as a humans we can recognize fairly easily the geometry of what we are touching, but we don't have a very good understanding of how this geometry corresponds to the force, whether this is shear forces or just normal force. And part of this is because the format of these images is not very human friendly. So something that, for example, we often do is that we compute this difference between the sensor without touch and the sensor when it's touching something, and this is a little bit more interpretable from a human, but not quite as good. Ultimately, there are also other labs so one question is really, what are the type of features that we want to get out of this sensor? And this is an open question. Other labs, we use mostly raw images because we have a machine learning pipeline, but for example at MIT they like to use optical flow, where they have markers and then they compute how these markers move. This is also not very interpretable, but it depends from what's your pipeline and what you care about. Yeah. Sorry.
Thank you very much for the talk, first of all. I guess as a follow-up to this, so you've been showing us these kind of images based on that have been generated by, I assume, the sensor that you've been passing around. I guess, how similar is that to the raw data output of other types of touch sensors? And are you expecting that we'll need to kind of standardize into something like this, or has everyone been arriving at roughly the same thing?
Different technologies use very different formats in this moment for output of the sensor. If you have a look at, this structure is very geometrical, for example, it's very prone to be 2D. But if you have capacitive or resistive technologies, it's not obvious that the output is even a 2D matrix. It can be some sort of complicated graph with complicated structure. I think that personally I find this type of output very satisfying because they are relatively easy to interpret, despite what I just answered before, compared to to a graph. But I don't think that this is necessarily going to be true in 5 years. I think that this is a question that we are just starting to investigate now, and probably in 10 years or 20 years we will know this is the standard format that everybody should be using, and at the moment we don't really know. Very importantly, this sensing, for example, human fingers are spectacular because they are made of many different types of organs that capture different aspects of touch. Something that, for example, is very important in human touch is vibrations, because high-frequency vibration tells us a lot about, for example, slippage of the object that you're touching, or the friction. And these sensors obviously don't have any sort of vibration sensing. So I expect that in the future we will see sensors that fuse multiple sensor modality in the same way that our fingers and our skin does. So the question is, how generalizable are the features learned if we change sensor or the hardness of the elastomer? The hardness of the elastomer is something that we did not investigate in the context of feature representation, although it would be very interesting. I suspect that that it would be hard for a model to know how hard is the gel. So if you tell him this is gel A or B or C, I think it would be very simple. But if it needs to infer the gel, the hardness of the gel, I don't think that this is possible from a single image. I would be surprised if this is the case. But if you have a standardized interaction, then it's likely that you can essentially infer this latent variable, which is the hardness of the gel. The temporal structure in interactions play a really important role. So static images don't tell you the whole story of what's happening when you're touching something. Yeah. Yes.
There's such things like that sensors, like I know for humans, we're in the water for a long time, getting able to adapt and get better tactile surface in water environments. Or they, like you said, it's such that you can optimize for different environments.
Yes. So the question is, can we adapt tactile sensors to different environments, roughly speaking? The answer is that I think this is a really interesting field, and I think we will see more of this. There is one piece of work from Toyota Research where they essentially have a small, they pump air essentially below their elastomer, and this allows them to control the stiffness of the gel. This is, I think, going in the direction of essentially being able to adapt on the fly the sensor, and I think we will see more of this because it's important. Being able, for example, to dynamically change the range of what you can measure would be super cool, but it's also mechanical. It's mostly mechanical design work, which typically is much slower than algorithm work. Every time you build a prototype, it takes 2 years. Yeah.
I guess slightly related to that, how sensitive is your sensor to like slight changes to, let's say, the camera or like temperature as the view angle changes a bit?
Yes.
How much does that change the way you
Yeah. So the question is, how sensitive is the sensor to small changes in the manufacturing process? Now, this is a really good question. With Digit, something that we tried very hard was to standardize the manufacturing so that the difference between different sensors from the same manufacturer batch are minimal. And I think that this is very largely true. I don't think that as a humans you can see a difference between two sensors that you buy from gel site. But to get there, we had to go through a lot of different iteration of the manufacturer. And something that was very interesting for me was that when we did some of the work at Berkeley about learning to grasp object in here and here, we were also using vision-based tactile sensors, but we had markers inside that we were using. Well, they were left over from the idea of using optical flow. We were not using optical flow, but we had markers. And what was happening was that throughout the whole data collection phase, once in a while the gel would wear out and we would change it, and the markers would be in slightly different positions. And what was this? This was essentially leading to the model, every time we would change a gel, to suddenly drop performance a lot. But very importantly, after changing 6 or 7 gel, the model essentially learned how to basically ignore the markers and was able to, to still be able to predict whether it's a successful grasp or not, even with these slight differences in the gel. Now, markers are arguably something that for this particular task is maybe not so relevant. So if we had differences in the geometry of the gel, maybe in the thickness, would that impact? We don't know, perhaps, probably. But ideally, if we reach the point where this is a standardized sensor, then we would have very low variability. in the same way that, you know, if you buy a cell phone, the cameras of different cell phones are roughly the same.
And even with different environmental conditions and wear and tear, temperature changes, and just like the gel touching things a lot, wearing out maybe.
There are some differences over time, over the gel consumptions. There are also very small variations because of temperature. But so far, compared to other technologies like capacitive or resistive, the effects that we see are minimal and are easily can easily be ignored for the actual task. Sorry. Yes.
Well, and then is there a mechanism for measuring wear and tear so it's time to change like that?
Yeah, typically for this is also backup slides. The type of how the failure mode for this type of tactile sensors is that at some point you essentially start having holes because the externally on the elastomer there is a reflective coating whose purpose is essentially to improve the internal reflection of light and to separate from external light sources. Now, in the moment when you start having this hole, is because this reflective coating is essentially detaching, and this will show up because you will suddenly have points where you can see through. You can, for example, see color of the object that you're touching, or you can see external light sources coming in. So it's fairly, as a humans, you recognize this fairly quickly. We haven't yet trained a model to recognize this, but I think it should be possible because it's very obvious.
You mentioned that your simulator is much faster than other, I guess, existing simulators. Was that specifically for the digit when you simulate that? And also, if you significantly increase the stiffness of that gel, then does that affect how fast you can simulate?
Okay, so the question is, first of all, does changing the stiffness of the gel change the speed of the simulator? And the second question was, sorry?
Actually, the first question was that specifically for your sensor?
Okay, and is the simulator specifically for digit? So the answer to this question is no. The simulator is, sorry, it actually uses sensor configuration files, essentially YAML file. So you can specify different geometries of sensors, and you can, in theory, if you want to build a sensor, you can first sort of prototype it here and test it. And in particular, the OmniTac, this is a sensor that was also published a couple of years ago, and it uses 5 different cameras inside and has this sort of omnidirectional sensing. And the cool thing is that the simulator was giving these sort of pinkish images, which is actually what a real sensor does, because the light is not as well distributed and uniform. The light sources are a little bit sparse. So it was very interesting to see that the simulator was actually giving similar output to what the real sensor was doing, although we never tested this before. So if you have a new sensor geometry, you can implement it and use it in theory. Now, regarding the simulation and hardness, what I should point out, and maybe it was not so obvious is the fact that we are not dealing with the dynamics of the contact. We essentially are delegating computing what is the actual physical dynamics, the physics of the contact, to whatever physics simulator you choose to use. So if you use something like PyBullet, which is a rigid body simulator, mostly, the physics of the contact will be completely off from reality, because you're simulating 2 rigid bodies touching each other, which of course is not true, because our sensor is soft, and likely also the other object might not be rigid, fully rigid. So the hardness will not, of the simulator here, will not influence the physics at all. What is going to influence is how the rendering of the deformation will be essentially converted into images, because in here you can essentially define, essentially in the renderer you can define again what is the dynamic range of forces that the simulator will produce. Yeah. Okay, so going forward a couple of decades, what do you think about skin? So in this moment, my hunch is that this type of technology of vision-based tactile sensors is not mature for skin yet. And the main problem here is that the way that we do essentially the sensing with the cameras requires some space between the cameras and the elastomer in order for the camera to be able to focus. I think that this is a technological problem, and maybe in a decade or two we will solve it and be able to essentially squeeze together the optics with the elastomer. But the minimum size that you can have nowadays is about 1.5 centimeter, and this is not going away immediately. So the other thing is maybe a little bit more philosophical, which is also, do we even need this type of high resolution on the skin? If you think about the human body, we have skin in a lot of places, but the resolution that our skin in the back of here has compared to the resolution of our finger is a very small fraction. And there are a lot of sort of psychological tests where people touch your back and say, oh, is this, what object is this? And it's extremely hard for people to know because they don't have so many sensors. So I think that it's likely in the near future that we will keep having two different technologies where the fingertip, you probably want to have something like a vision-based tactile sensor which gives you very rich, very detailed information, while for the skin you want to have something that maybe has a fraction of the resolution, but it's easy to manufacture for large patches, and you just integrate the two type of sensors. And in this spirit, for example, at Facebook, there is another researcher, Tess Hellenbrecher, and she's been working on making skin, and there is a paper called Reskin, where they essentially detail the design of a low-cost reusable skin that can be produced with, for large patches. It doesn't quite have the same resolution, but as I said, you probably don't need it for the whole kinematic structure of the robot. One more question.
One more forward-looking question. So, for example, the task that we can't do right now, I'm thinking of tying a knot in a thread, some sewing task. Do you think the perception side is solved by gel side, and we just need to get the actuators there, or do you think we still need improvements in the touch sensing technology to accomplish that sort of task?
I think that for most tasks, having tactile sensing will help. Tasks that have interaction and fine manipulation. One limitation of the sensors that you've seen around the digit is still the form factor. In my personal opinion, we are still a little bit far away from the form factor of a human finger. This is still a relatively bulk sensor. It doesn't have the nice sort of curved surface that a human finger has. So some of the tasks that might require this curvature arguably are probably difficult with a digit. But I do think that in the coming years we will get there, and ultimately, if I think 5 years into the future, I think it's likely that we will have a sensor which is the size of a pinky, the shape of a pinky. It's mostly a mechanical design problem, which is super hard, but it's solvable, I think, with the current technology. All right. Thank you very much for. I don't know if there is any question online or if there is a way.
There are any questions.
Okay.
You had good viewers online, but they were just very quiet.
No.
Yeah, Roberto.
Roberto, thanks so much. Thanks everyone for attending. I think we have now a meet and greet, so if you want to chat more with Roberto or with each other, please stay here. I think we have some snacks in the back.